Hi, and welcome to this quick review of the structure of benzene. So because many of benzene's properties are different or anomalous in some way to normal hydrocarbons, we're going to focus on the origins of the structural model that we currently use to try and explain this. So these properties are sufficiently different to those we find in normal aliphatic hydrocarbons to justify the creation and existence of another branch of organic chemistry called aromatic chemistry, which concerns the properties and behaviour of any compound containing a benzene ring. So there's a number of notable people involved in the development of our current model for benzene. So we've known about benzene for quite some time. In 1825 or thereabouts, Michael Faraday used percentage by mass data to establish the molecular formula of the compound as C6H6. 40 years later, Auguste von Kekule proposed a ring structure now known as the Kekule model. So the story goes that Kekule was inspired by a dream about snakes chasing their tails, and his model has alternating carbon single carbon bonds and carbon double carbon bonds. It was also proposed that the position of the double bonds could alternate. So by movement of electron pairs, you could go from one set of positions of the double bonds to another and back and forth. So those that proposed this idea suggested that benzene had what's called a resonance structure. But this meant that people were unclear about the positions of the double bonds. And what started to happen is we started to disprove Kekule's model. So in 1929, Professor Kathleen Lonsdale was able to prove using X-ray crystallography that all carbon-carbon bonds in benzene were the same length and between the known lengths of carbon-carbon single and carbon-carbon double bonds. So it wasn't just this evidence that was able to disprove Kekule's model. We also discovered that benzene doesn't react with bromine as any compound containing carbon-carbon double bonds would do. There's also some thermodynamic evidence, and that's that the enthalpy of hydrogenation of benzene is less exothermic than we'd expect for a compound that allegedly has 3 carbon-carbon double bonds. So if we take the standard enthalpy of hydrogenation of a carbon-carbon double bond is minus 120 kilojoules per mole to the minus 1. So if we take the arrow on the y-axis to mean increasingly exothermic, you can see that as you go through 1, 2 and 3 carbon-carbon double bonds, you have an increasing amount of energy that is released. So thinking about the Kekule model with its 3 carbon-carbon double bonds, you'd expect to have a hydrogenation enthalpy of minus 360 kilojoules per mole. But when we actually hydrogenate benzene, what happens is we find that it's measured as minus 208 kilojoules per mole to the minus 1. This makes it 152 kilojoules per mole less exothermic than expected. So this means that benzene's structure must be more stable than one containing 3 carbon-carbon double bonds. So in the face of all this evidence, a new model had to be proposed, and the current model we use is called the delocalised pi system model. So the delocalised pi system model is the model we currently used. And there's a few features that you need to be able to remember and reproduce in exams. We have 6 carbon atoms in a planar ring structure. The shape of all the bonds is trigonal planar and 120-degree bond angles throughout, with each carbon atom having 3 sigma bonds and 1 pi bond. The p orbitals overlap sideways all around the ring, above and below, and each carbon atom's 4th electron is delocalised around this ring structure. So you will be asked to draw this in exams. So I'm going to show you 2 possible ways of doing it, and you can choose which one suits you best. So you start by drawing a slightly flattened hexagonal ring of carbon atoms. You then add the hydrogens, roughly with the bonds at around 120 degrees. You draw in teardrop-shaped p orbitals pointing up from each carbon, not forgetting the rest of the orbitals figure of 8 shape. And I've just popped a reminder in the bottom left of the screen to show you what a p orbital looks like, or at least the shape that we use to assign to it. So you draw dotted lines between the p orbitals above, and obviously below as well. So what you're trying to aim for is a little bit like a layer cake. Obviously you need to label it so the examiner can see exactly what each part of your diagram represents. Now that method is my personal preference, but there is another way of doing it that will also get you the marks in the exam. So you start as before, but this time what you can do is draw in annular rings. So if you imagine a chopped tree trunk, you draw one circle inside the other. So you do that above and below. And as before, you need to label it. And notice that what you must have every time is the mention of sideways overlap of p orbitals. That's very, very important that you show them that you understand that. So let's now move on to how to name benzene compounds. So it's in fact very similar to naming alicyclic hydrocarbons. So this is obviously benzene. Now it could also be written another way. So both these versions of benzene are acceptable in exams, but the circle within the hexagon on the left represents the delocalised pi system we've just talked about, so that's going to be the one that I'm going to use for the rest of this clip. So it shouldn't be too difficult to see how all those structures are named. There's a prefix to the name, and the prefix is either methyl, ethyl, chloro, or bromo in these cases. There's lots of different possibilities, obviously. Another one you'll definitely come across during the course of your A-level chemistry is nitrobenzene, so I popped that one in there as well, so you can see what that would look like. What happens if you start adding more than one substituent? So obviously you'll need to assign numbers to the carbons in the benzene ring. So you number the carbons so as to arrive at the lowest possible number within your name. So you can count right or left, it doesn't really matter. So not only must you number the carbons so as to arrive at the lowest possible numbers, but the naming of the ring is based, where possible, on the presence of any methyl groups or ethyl groups if they're there. And substituents appear in the name in alphabetical order. There's lots and lots of different combinations that I could go through. I could sit here for 3 hours going through all the different combinations, and I'd probably get myself tied up in knots as well. I've probably taken it as far as it needs to be taken for A-level for now. So if you do come across any strange ones, it's best to ask your teacher, because they can check it for you, whether you need to know it for your specification. At the end of the day, you've got to keep it in perspective. Naming will only ever be 1 mark in an exam anyway. It's not going to be 5 or 6 marks. So if you get it slightly wrong and you don't get the mark, and so what? So it's best to try and keep it in perspective like that. Okay, so that takes us to the end of this quick review of the structure of benzene and some introduction to the naming of aromatics. But it's best to go away and try some now, as always, to try and get your head around it and start to get comfortable with it. So until next time, thanks a lot and see you soon.